And in our local universe, although we can detect some individual sources above redshift 3, these sources are typically too faint for having large number statistics, and therefore we can make galaxy surveys up to, let's say, redshift 3. We can count the number of galaxies in each voxel, plot the matter power spectrum, and extract from it cosmological parameters. Then, on the other end of the redshift axis, we have recombination at redshift 1100, and so we can measure the spatial fluctuations in the CMB, plot the CMB power spectrum, and again extract the cosmological parameters. In between, however, there is a huge volume of our universe where these two observables can tell us very little about what's going on. And so the 2170 signal.
You're aiming to do this in half an hour, right?
Yes.
Okay.
Yes, half an hour. And the 2170 signal presents an opportunity to access this incredible redshift range between recombination and redshift 6. And the reason why it cannot probe lower redshifts is because the origin of the 2170 signal comes from neutral hydrogen atoms, which were much less abundant after the ionization took place around redshift 6. But there is another reason for why we can benefit from the 2170 signal for cosmological studies, and it has to do with scales. So the amplitude of the fluctuations of the CMB decay at small scales because of photon diffusion from hot spots to cold spots. This is what known as the silk damping, and it happens at scales below the CMB scale. But in contrast, the 2170 signal doesn't suffer from the damping, and instead the amplitude of its fluctuations start to decay only at the gene scale, which is orders of magnitude below the CMB scale. So these two features of the 2170 signal, access to a lot more redshifts and much smaller scales, will hopefully enable us to expand our knowledge about the universe more than what the CMB has already taught us. And so I'm not the first person to use the 2170 signal to study dark matter. Many people have done it before me, and traditionally studies of the 2170 signal either focused on high redshifts or at low redshifts. And at high redshifts, the spatial fluctuations in the signal are very small. They're tiny. And therefore, linear perturbation theory can be applied in this regime. But in low redshifts, once galaxies have formed, these fluctuations become highly nonlinear. And so semi-numerical codes like 21CM fast have become very popular tools in investigating these nonlinear fluctuations. Now, what I do in my research, however, is to study both regimes of high redshifts and low redshifts, and I do that with a code I call 21CM first class, or in short, first class. And as you can see, first class is sort of an extension to 21CM fast, and it can begin its calculation from recombination. But it has another advantage. So the reason why we call our code first class, besides of PR obviously, is because we actually use a code called class before we run 21CM fast. And so class is mostly famous for being able to compute the CMB anisotropic power spectrum, but we also use it to generate the consistent initial conditions for 21CM fast. So whenever we study a new dark matter model with first class, we also modify class to get the correct initial conditions for 21CM fast, and then our code consistently evolves the box from recombination all the way to lower redshifts. And because our code uses a box, it can even be used to study models which exhibit nonlinearities already at high redshifts. And finally, because the outputs of first class are both the CMB anisotropic power spectrum and the 2170 signal, these two observables can be combined to relax. Wait, just a second. These two observables can be combined to relax the degeneracies and improve the constraints on the dark matter models that we set.
I don't know too much about either code, so like if you just use 21CM fast, what's the initial condition? Like, is there a default initial condition, or?
So it starts the calculation at redshift 35.
Yeah.
And yeah, and it starts with homogeneous boxes for the temperature field and the ionization field. It does start with an inhomogeneous box for the density field. right? But so we use sort of the same initial conditions, but at a combination. And then when we evolve the box through that epoch, we end up with an inhomogeneous boxes for the temperature and ionization fields at redshift 35. Right, okay, so I have many introductory slides here for the 21 centimeter signal, but I don't have a lot of time, so I'm going to skip through them very, very quickly. Sorry about that. So this is the slide I want to get to. The 21 centimeter signal is given by sort of the expression above. It's T21. It's sort of a temperature. And it is given by several physical quantities. One of them is XH1, which is the neutral hydrogen recombination. And it also depends on T gamma, the CMD temperature, and also on Ts. This is the spin temperature, and you can see its evolution here on the left-hand side. And so once I combine all these curves together, I end up with this beautiful curve for the 21 centimeter signal as a function of redshift. And the nice thing about this curve is that it contains many features, and we can relate each one of them to a different cosmological epoch. So for example, the first chart here on the right-hand side corresponds to the Dark Ages, while this peak here marks the onset of the cosmic dawn, when the first stars were born. And then this rise here corresponds to the epoch of X-ray heating, and the last part of the signal corresponds to reionization, and afterwards the signal is dead, simply because there is much less neutral hydrogen in the universe. Now, although this is how we expect the signal to look qualitatively, quantitatively, everything that happens at the cosmic dawn or afterwards is under a lot of uncertainty, because key physical properties, such as the X-ray heating rate, the reionization rate, the Lyman alpha flux, they all highly depend on the assumed astrophysical model. And so, even though we have yet to measure the signal at the Dark Ages, we think we understand in theory how that signal looks like at that epoch. And this is because this absorption profile doesn't depend on any complicated astrophysics, only on pure cosmology. And an important property to remember regarding 21 centimeter signal is that not only we can study the temporal evolution of the global signal, that is the sky average signal, we can also study the spatial fluctuations, like I'm showing you here. So this is the second time I'm showing this figure already. And for example, you can see here by the white regions, the formation of ionized bubbles that grow as we move towards lower redshifts.
So it depends on what you're putting in, I guess, about the reionization.
Yeah, absolutely. Yeah, so there is a model for reionization that is implemented inside. It is based on the calculation themselves. They based on excursion set algorithm to generate these bubbles.
But for example, does it have AGN formation and stuff like that?
Oh no. It doesn't go into these scales for the AGN. It works on the cells. The cells of the box are larger.
How big are the cells?
So you could
physically, right? Typically, like in
typically, so here about one MPC.
Right, but if you had an early AGN at redshift of 7, let's say, it would be making impacts on those scales, wouldn't it?
I mean, I think that would mostly live in like there's like parameters about like the radiation, like typical radiation field and stuff coming out of galaxies. Like the heating, there's like heating rates and ionization rates and things that are tuned.
I was thinking about the inhomogeneities.
Yeah, so there are numbers that are tuned in 21 centimeter fast to kind of represent the average effect of quasars, and then that's like stochastically sampled with the density field to produce. It doesn't tend to resolve, at least base 21 centimeter fast doesn't tend to
I'm
resolve.
just curious because there's all
objects.
this recent stories about much more high redshift supermassive black holes than we did thought.
Thanks, Patrick. I couldn't explain it better myself. All right, so in order to understand why 21 centimeter signal has the potential to probe dark matter beyond the standard model. So let us look on this cartoon of the global signal during the cosmic dawn. And the black curve here is supposed to correspond to lambda CDM, which is quite ambiguous because even with the same set of cosmological parameters, the signal may look completely different if we change the underlying astrophysical model or its associated parameters. And just so you get a sense for how the signal depends on the astrophysics, these are all the signals that you could obtain by just simply changing the astrophysical parameters. So it can literally be anything. And for the sake of simplicity, let us assume that we agree both on the model, on the astrophysical model and its parameters. And then, if in the experiment we witness a signal which is much deeper than what expected, that may imply that something cools down the IGM. And that thing could be, for example, scattering dark matter, which I'm going to talk later in one of these talks.
Wait, those curves you showed on the previous slide, were they like within experimental constraints, or is that just like randomly varying? No, that must be just like randomly varying astrophysical parameters in crazy ways.
Yeah, it's the second option. You have like a bunch of, you have a lot of astrophysical parameters.
What's like the error bar in that line typically?
The error bar? Okay, so it depends on the experiment.
Observe error.
So it's a good question. I'll have a slide that shows error bars later.
But all of these are possible versions, if I understood what you said.
Yes.
That is to say, it's not like some of those lines are excluded because we know.
Right, we know nothing.
Those are
We know
all
nothing about what's going on.
scenarios.
Yeah, they can all be real. Okay,
I think that
in
was
principle.
it.
Okay,
Yeah.
sure. Okay.
Okay, so we got that. If on the other hand we see a signal which is shallower than what we expected, that means that something heats up the IGM. While if we find the minimum of the signal to be located at a higher redshift, that means that something speeds up structure formation. While if the minimum of the signal is located at a lower redshift, that means that something delays structure formation. Now, of course, the challenge would be, besides detecting the signal itself, to also be able to remove degeneracies between the dark matter parameters and the other cosmological and astrophysical parameters. And for that reason, we need more information like these spatial fluctuations and not just the global signal. And to demonstrate the constraining power that the 21 centimeter signal would have in searching for exotic dark matter, let us consider fuzzy dark matter, or FDM, as an example. So what is fuzzy dark matter? It can be mathematically described by this simple Lagrangian of a simple real scalar field. Here phi, this is the FDM scalar field, and MFDM, this is the mass of the FDM particle. And as you can see, it is extremely tiny, cannot be greater than 10 to the minus 20 eV or less than 10 to the minus 27 eV for reasons that will become clear shortly. And as we will see, fuzzy dark matter is closely related to ultralight axions, which is why I write now this Lagrangian with MA instead of MFDM. And one of the few things that we can do with Lagrangians is to find the equation of motion, which in this case is just the Klein-Gordon equation. But keep in mind that this box operator that you're seeing here has to be evaluated in FRW background. And so eventually we end up with the following equation of motion for the homogeneous part of phi. And this equation of motion is pretty simple because it's basically the same equation of motion for a damped harmonic oscillator. So at early times, when the Hubble parameter is much greater than the mass of the axion, then the term in the middle dominates, and then we see that the field slowly rolls down, the potential. But at late times, when the Hubble parameter is much less than the mass of the axion, then we end up with an equation of motion for a simple harmonic oscillator, and then the field oscillates at the vicinity of the minimum. And another thing that we can do with the Lagrangians is to derive the energy momentum tensor and extract from it the energy density and pressure that are associated with the field phi. And at early times, when the derivative of the field is very small, we see that the equation of state is roughly -1, which means that at early times, the field behaves as dark energy. But at late times, we saw that the field oscillates rapidly around the minimum. So people, what they usually do is that they take the WKB approximation, they write the field in the following form, they plug it back into the equation of motion, And then they find that the energy density goes like the scale factor to the minus 3, which implies that at late times the field behaves as matter, as dark matter, rather as dark energy. So I want to show you that with some cool plots from Dodi Marshall's paper. So here we see that indeed at early times the field is sort of stuck at its initial value because of the Hubble friction it experiences, but at late times it oscillates around 0. And the special moment when the field when the evolution of the field changes its behavior from this to that, indeed corresponds to the time when the Hubble parameter becomes comparable with the mass of the axion. And regarding the equation of state, so we see indeed that at early times it's constant -1, like dark energy, but at late times it oscillates very rapidly. But we can average over these fast oscillations to end up with an equation of state of W equals 0, which is like dark matter. And we can also see that from the last panel here, where now I'm showing you the energy density of the field. So at early times,
Y is not the.
sorry.
I'm trying to relate this to real redshifts for a given axion mass.
Yeah.
I'm having trouble. These are just, the A sub I hasn't been specified, I guess. And.
Yeah, A sub I
So-
hasn't been specified, that's true.
But I mean, am I supposed to read this as the regular scale factor with respect?
Oh,
to
yeah,
scale
yeah,
factor
absolutely.
count?
Yeah, I can
So we're
remember
talking about
myself
like
what is A
redshifts
sub
of
I.
10 or 20 or something, we would be, or maybe 100, we would be in the middle of this.
Yeah, so it depends on the mass of the axion.
Right, but I'm just curious what you took. You're talking about fuzzy dark matter, so,
Yes, yes.
and so what's this typical of, for what mass would this be?
Oh, so for fuzzy dark matter, it's between 10 to the minus 27 eV to 10 to the minus 21 eV. These are
Yes, I know that. I'm asking on this. Translate it, please, this structure to redshift for me. Or scale factor, I don't care which, but I want to know,
So-
you know, is this in the,
So it happens after matter radiation equality. Okay,
The dashed line is where the mass is equal to Hubble, and so for the masses that he's taking, so 10 minus 27 eV and above, it's before matter radiation equality.
Exactly.
okay, thank you. That's what, I just didn't remember the numbers well enough.
Thank you. And I
Thank
was about to say that right here in this slide.
Oh,
So great question. So the transition from dark energy to dark matter happens when Hubble becomes comparable to MA. And if MA is less than 10 to the minus 27 eV, the transition happens after matter radiation equality. And if the mass of the axion is less than the current value of Hubble, that means that the transition hasn't occurred yet. Which means that.
Such light axions as that, I thought were really ruled out by things like
So I'm going to show.
galaxies.
So I'm going to show the constraints that we have on axions or fuzzy dark matter in this range for masses that are greater than this value. I have a slide for that.
People often say 10 to the minus 22, right? That it needs to be bigger than that.
That it used to be greater than 10 to the minus 22.
Right, that otherwise we wouldn't have.
So we will see. We will see. Okay. But anyway, so we refer to axions which are greater than this mass as fuzzy dark matter, because otherwise the axion field behaves as dark energy for too long, for too much time. So let's combine what we have discussed so far. How does fuzzy dark matter affect the 2170 signal? So consider a fuzzy dark matter particle with mass that is less than 10 to the minus 21 eV, and that particle has an astronomically large de Broglie wavelength which is greater than 1 kiloparsec. And so according to quantum mechanics, the particle cannot be localized within this volume, within scales that are below the de Broglie wavelength. And in fact, in smaller scales, the fuzzy dark matter behaves more like a wave rather than as a particle. And the implication of this wave-like nature is that small scales at large scale structures are now smeared. And this serves as a sort of visual explanation for why fuzzy dark matter can solve the core cost problem, as it smooths the density profile of dark matter halos at small scales. Yes.
As you're making these predictions, you're tuning the misalignment angle to give you the dark matter density of today. Like if you have in mind that axion, you get your DM from misalignment mechanism, right?
Misalignment mechanism. So I'm not very familiar.
Maybe we should just let him assume that it's
Okay,
the dark
yeah,
matter
yeah.
and not ask how that could be.
Right. So now what I'm going to show you now at this plot is the is the ratio between the matter power spectrum in an FDM universe and a matter power spectrum in lambda CDM as a function of the wave number k. So power in the fuzzy dark matter universe, power in small scales is suppressed by orders of magnitude because of the wave-like nature of the fuzzy dark matter, and this suppression effect becomes more and more pronounced as we decrease the mass of the FDM particle, and then power in larger scales becomes suppressed as well. Now, keep in mind that the suppression effect corresponds to the case where the fuzzy dark matter comprises 30% out of the total dark matter, and obviously this suppression effect becomes weaker when we decrease the FDM fraction. Right, so we saw that fuzzy dark matter washes out structural formation in small scales, and therefore there is less small mass dark matter halos, and as a result the star formation rate is smaller, which leads to the cosmic dawn being delayed, and as a consequence the 2170 signal is delayed as well. So let me show you just that. Here I've plotted the 2170 signal from redshift 36, and the black curve here corresponds to lambda CDM, while I assume some astrophysical model from 2170 fast. And now, if I introduce fuzzy dark matter, so like I said, the suppression in the matter power spectrum causes a delay in the signal, and this delay effect becomes stronger as we decrease the mass of the FDM particle, but it becomes weaker when we consider a smaller fraction for the fuzzy dark matter. Now, remember that the 2170 signal is more than just a global signal, and we can also study the spatial fluctuations, which contain much more information. And then the statistical, theoretical statistics of these fluctuations can then be confronted with data that is coming from experiments like HERA. So this is how HERA looks like. Just 7 years ago, it's a rather old photo of HERA. And HERA is basically a radio interferometer made of 14 meters wide dishes. And below you can see how HERA looks like once its construction is complete. So I forgot to mention, HERA measures what's known as the 2170 power spectrum, which is essentially the Fourier transform of the 2-point correlation function. So regarding the question, so before I show you how HERA will be sensitive to different FDM masses, I'd like to show the current constraints that we have on this model. And so the main constraints that we have comes from the CMB. And if we add on top of that data that is coming from large-scale surveys like BOSS, obviously the constraints improve. And we also have constraints coming from galaxy weak lengthening, but they only apply to FDM fraction of 100%. Then, on heavier masses, we also have constraints coming from the Lamarck force. Now, I should say that there are more constraints in the literature, but nevertheless, these are the main ones. And as you can see, they allow this window where fuzzy dark matter can still exist in large portions. So coming back to our 2170 discussion, we found that HERA will be sensitive enough to probe fuzzy dark matter with a fraction of a percent over a wide mass range that includes also this poorly constrained region of intermediate FDM masses. And for comparison, you can see that HERA will be competitive with CMB stage 4 and even better at some regions in the parameter space. And let me just say that this solid red line here corresponds to HERA in its design sensitivity, but we also found that in the near future, HERA will be able to probe or rule out FDM of fractions of the order of 10%.
You say near, in the near future, what is HERA's status?
Yeah,
I
so
just
it's,
have not followed it.
yeah, so it started to make measurements. Right now, it mostly can give upper bounds for the power spectrum, but they also made an analysis where they put constraints on the X-ray luminosity of those stars.
So you said in the near future, does that mean like next year?
In the near,
or-
okay, so
I was just trying to get a scale on.
okay, so suppose like this is sort of the near future, just
That's
in the,
presently now. not-
yeah, this is sort of like the present, and
2016.
this
I'm
is
sorry.
and this is the design sensitivity once you have all the antennas and all.
I'm sorry, I thought you were saying that was it in 2016, excuse me.
In 2016.
I'm sorry, and yes, 2016, this is 2023. But, so it's not 7 years ago, it's today, the upper picture.
No, the upper picture. No, the upper picture was taken from that paper like 7 years ago.
Okay,
Okay, but we are still. It doesn't look like that.
I'm just asking how far is it from looking like that? Is it like almost there, or is it?
I would say
10%?
I can't remember the exact numbers. Also, like how many
No,
antennas.
no, just
that's-
approximately.
Yeah,
Is it
yeah. So,
almost done?
so something like I would say half, more or less. Okay, so I don't. How much time do I have?
Start a little bit late with 3 more minutes for 30 minutes.
3 more minutes? Yeah, all right. So the next model that I'd like to talk about is scattering dark matter. This is a model where dark matter particles elastically scatter off standard model particles. Right, and I don't have time to go over all of that. I'll just say that this model has some free parameter that characterize the cross-section of the direct interaction between the dark matter particles and the standard model particles. So you can see how the temperature of the gas of the IgM goes like when we consider a zero cross-section, like in lambda CDM. But when I increase the when I now consider a finite cross-section, then the direct interaction of the dark matter and the standard model particles make the temperature to decrease, and when I now amplify the cross section by an order of magnitude, then the cooling effect is enhanced. Right. So error bars, I think was you first, right? So now we can see the error bars. You can see what happens when we consider what happens to the 2170 signal, either the global signal or the power spectrum, when we consider different kinds of cross sections. Right, and as was in the case for fuzzy dark matter, the most stringent constraints on this model, they come from the CMB. So here you can see how the maximum cross section allowed by the Planck's measurements, as well as projections to CMB stage 4. And the idea is that what I wanted to show you earlier is that it seems like HERA will be able to place tighter constraints on this model. And yes, HERA will be able to do that, but in order to derive reliable forecasts, we need to vary all the relevant parameters in this problem and study their degeneracies. So here you can see 1 sigma and 2 sigma forecasts for HERA's constraining power for the cosmological parameters in an SDM universe. And yeah, so I should stress that in order to derive these forecasts, we also had to marginalize the astrophysical parameters, which I'm not showing you here, but now I'm showing you the same focus as before, but now I have demarginalized one of the astrophysical parameters. This is Lx. This parameter denotes the X-ray luminosity that is coming from pop-2 stars. And I think it's pretty cool that we can see that this parameter is degenerate with the SDM cross-section, okay, which is sort of makes sense if you think about it, because if you simultaneously increase by the same amount the X-ray heating rate and the SDM cross-section, which results in extra cooling, then these two effects roughly cancel each other. And so therefore, these two parameters exhibit a positive correlation. Right, and so now I've remarginalized over this parameter, over this LX parameter, and now we can see from the bottom row that if indeed SDM with this specific cross-section does exist, then HERA will be HERA indeed will be able to probe it within 2 sigma confidence level. And in this project, we've also made a joint analysis between 21 centimeter and CMB, and here the CMB forecast correspond to CMB stage 4, and apparently the CMB won't help in relaxing all the degeneracies in all the cosmological parameters, specifically not for the SDM cross-section, but its inclusion in the analysis may lead to pinpoint some of the other cosmological parameters like A sub S and omega B with an unprecedented level of precision. And finally, it's also interesting to compare the performance of HERA and CMB stage 4 for constraining the cosmological parameters. So while CMB stage 4 will have a better constraining power for most cosmological parameters, our analysis shows that HERA will have the upper hand when it comes to constraining the SDM cross-section and omega m. And the reason why HERA will be so sensitive to omega m is because, so I didn't say it earlier, but here we've assumed that all the dark matter in the universe is in the form of this SDM. And because the 21 centimeter signal is so sensitive to this model, to this SDM, it means that it is also sensitive to its abundance, which is controlled by omega m. And you can also see by this figure, by the way, that while CMB stage 4 will barely be able to detect this SDM if it exists within 1 sigma confidence level, HERA will be able to do so within 2 sigma confidence level, which is a nice result, I think. Okay, so this is my summary slide. These are the main points that I'd like to take from this talk. I'll leave it in the background, and I say that for future work, we plan to use HERA's current data to constrain fuzzy dark matter and scattering dark matter. And we can also use the 21 centimeter signal to study other dark matter models like decaying dark matter, self-annihilating dark matter, and even primordial black holes. And that's it. Thank you very much for attention.
So if you had just used regular vanilla class and 21 centimeter fast without all the nice self-consistency, how wrong would you expect to be? Like what's the bias you get from using the wrong initial conditions with 21 centimeter basically?
Yeah, good question. So
unfortunately,
I don't have a hidden slide that shows you the differences, but it can cause you differences. Like right, because if you want to make such an analysis, right, you want to be consistent and you want to start with the proper initial conditions. No, it does affect the signal, but I can't unfortunately I don't have a figure like that, and I can't throw you a number.
but enough to matter on the scale of these uncertainties.
Absolutely.
You showed us those curves of the sort of astrophysical variance and what goes
Oh,
on.
sorry, say it again, please.
Of the sort of variance depending on your astrophysics model of what's going on at sort of cosmic dawn, that era. And I wondered, you picked something, but you haven't, your error bars don't include that uncertainty, is that correct?
So I'm trying to get the slide that you're talking about. I think maybe here?
No.
Well, there were all these
All the blue
curves.
lines that he was asking about.
Yeah, I'll try to get there. I think it was this one.
That one, yeah.
Yeah,
So
sorry.
how did you deal with this uncertainty? in your predicted error ellipses.
Right, right. So, like I said, you can get all these curves if you change the
No,
astrophysical
I'm
parameters.
saying in your error ellipses on the last slides.
Yeah, yeah,
Showing the sensitivity of HERA
yeah, yeah.
and HERA plus CMB.
Mm-hmm.
How did you create this uncertainty? Did you just pick the black line?
No,
Or
no, no,
did you-
no, absolutely not. So this is what I try to explain. Maybe I was failed in doing so. But we had to consider the variation, the uncertainty in the astrophysical parameters. So we had to vary them as part of our
Okay,
analysis.
great. So that's already in your.
Yes,
error.
yes,
Yeah.
absolutely,
Terrific.
because it really matters,
Yeah,
right?
yeah.
But it's assuming you've then put an actual like HERA sensitivity on
Yes.
this as opposed to the current thing, which
Yes.
will rule out many more curves.
Right.
Thank you.
Cool. Let's thank Jordan again.
All right.
Yeah, quickly. Sure. Yeah.